Everybody, I thought it'd be a good idea to take a look at the question number 6 from the 2024 AP Chemistry FRQ. Let's just jump right in. Okay, so the first question is asking, how do we know this is second order with respect to NO2? Second order reaction, this is the rate equation. Okay, yep, I see that this is the claim for the equation. And so I'm going to look here at the straight line plot, which this is usually used to determine the rate constant. And what I see here that's of interest are units, right? So we have time on the x, and we have 1 over concentration on the y, and bells kind of go off in my head, ding, 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 that this is in fact, yes, second order. And then, you know, this is kind of a step-by-step guide walkthrough, so that this writing won't be kind of perfect, but what you can say is that units for straight line plot agree. You know, something simple like that. I think that's perfectly fine, because that's really what they're looking for. They see that, or you see this kind of straight line plot, and you're like, okay, yeah, I see that these units, I've seen this before. Yep, that's second order. Okay. At a certain point in the reaction, the rate of disappearance of NO2 is determined to be blah. Okay, some nasty small number. Determine the rate of appearance. Okay, I see rate of disappearance, I see rate of appearance. I think it's time to go to look at the stoichiometric relationship. 2 NO2 makes 1 O2. For every 2 of these guys, for every 2 of this, 1 O2. So that's kind of the thing, what the relationship is in words. What does that mean? Well, we can just divide this by 2 to get the rate of appearance. So rate equals 6.52 times 10 to the negative 7. Don't forget your units. I think you can lose points for that. And you can use a calculator for this, I imagine, on the AP Chemistry exam. If I remember correctly, I used a calculator for mine. Or you can kind of go through the process of dividing this. I think it's 3.26 times 10 to the negative 7 moles per second. Or maybe it's molarity per second. Yeah, it'd be molarity per second, concentration per second. So, and I'll just write O2. Appearance, again, just really, this is quite simple math, or quite quick math, but the biggest thing is just look at your stoichiometric coefficients. That's how you get this part. All right, oxidized, I see this, E minus, losing E minus, oil rig, oxidation is losing. Okay, draw Lewis diagram structure. So I recall that nitrogen has 5 valence electrons, oxygen has 6 valence electrons. You can see that from the periodic table based on what column it's in. And we also see that we have a plus sign, so we have to subtract 1 electron. So in order to figure out the total number of electrons, we have 5 plus 6 times 2 because they're 2, and then we subtract 1, which equals 5 plus 12, which is 17, so 16 electrons in total. And I'm going to take a quick look at this. Visually, we can kind of see how we just remove this electron, right? You oxidize one, it seems like this is the easiest one to lose. And then what happens here is that we can think about this lone pair kind of doubling down, coming down here to form a double bond. And so let me draw that out and see kind of what shapes out. So the octet rule is satisfied for this nitrogen now. Initially it wasn't, it was really unhappy. So this looks like a good diagram, and we'll notice that we'll put in all these electrons, making a mistake here, sorry. We can put in these electrons, we can count it all up, and surprise, surprise, it does equal 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And what we can also do is think about the charges. Oxygen valence electron 6, so 1, 2, 3, 4, 5, 6, right? Only one of these, 1, 2, 3, 4, 5, 6. So the oxygens are happy, and then nitrogen 1, 2, 3, 4. It has 5 valence electrons minus 4 associated electrons. It has a plus 1 charge, and plus 1 agrees with that. So this is our Lewis diagram. I'll just write it like that to keep it simple, and we can just put 2 check marks here because we are all good. We show the bonding electrons, we show the non-bonding electrons, so we're all good. Okay, so now looking at the bond angles, great. I'm thinking Vesper, I'm thinking, you know, hybridization, I'm thinking all these kind of great things. Are they different from each other? Well, we can look at, we'll start with this one, right? So I'll erase this because this is not reflected in the question. I see, one electron species. I like to call it another electron species. So I see 3 electron species. This looks kind of, in a way, bent. Outright like bent like structure. The bond angles, something along the lines of 120. About, I think it's worthwhile to write will deviate, because you've got that radical there that's going to really change that up. And you also have a double bond. It's not going to be a perfect kind of sp2 hybridization structure, but something about 120. And then you have this NO2 plus, and you only really see these two. There's no lone pair here. That's not the case. And you only have 2 electron species, and this kind of bells go off my head like, okay, this is sp hybridized. And with sp hybridization, we can really quickly recall that it's a 180-degree bond angle. And we can even kind of try and get some brownie points by saying this is linear. Get the brownie points, get that reviewer thinking that you know what you're talking about, because you do. This is a linear structure, and yes, these are totally different diff angles. So, right, we write the different angles, we write, the angles, and then make sure at the top, right, we answer the darn question. Do we agree or disagree? We agree. Or I guess you write I agree. We agree, and then you can include this supplementary information, make it cleaner, make it neater, maybe write a bit more, but that's how you'll answer it. And so that is all it is for question 6. Yep, this is question 7. I'll go on that in another video. Hope this was helpful. Please like, comment, subscribe if you have any questions, and yeah, have a nice one.